today what we'll be discussing is introduction to hardware pen testing. What exactly it is, how do we pen test it, and what exactly goes on behind the scenes. We use hardware devices on a daily basis. We don't generally think about the fact that yes, even these devices need to be pen tests, and security audits need to be conducted on these devices as well. You might think about that we'll be pen testing web applications and Active Directory. All of that is very well known. Not many people do it. Not many people understand how it works. So today we'll be giving you a demo and an introduction to how something like this could be carried out. So basically, hardware pen testing is something that will get you interested and get you aware of the fact that there are a lot many more devices that then you might realize. Like sitting out here, what you would think is electronic devices. What you would think? We have a computer, we have a phone, we have an iPad. That's about it. That's the extent of what people think when it comes to anything that could be pen test or softwares or even hardwares as well. Like he said, we are going to have an iOS bootcamp. You guys are going to learn a lot from there as well. So iOS devices as well, you would count that in a subject of pen testing. But what you would not is a router, maybe that camera over there, maybe lights, smart lights, Alexa or Google Homes or things like that. That is basically IoT. IoT is Internet of Things devices, general small purpose devices that not many people think about. It is just something that you get and you forget about it. You think it's just going to work. It generally does work, but there are a lot of things that could go wrong and a lot of issues that could be present in that device. So today we'll be discussing that topic, and today we'll be discussing about a few vulnerabilities that you might come across, or just to get you started on how embedded devices, as in one second, I'll just show you this. Yeah. So this router, I'm just taking this as an example because this is very relatable to everyone and everybody has a router at their home. Instead of this device, you could also be, the same thing could be applied to a bulb, a smart bulb, to Alexa, to even medical devices as in the bed that you are on, the one that goes up and down. That is also an IoT device. It is also connected to the internet most of the time. And even devices that can, you see that screen where your blood sugar and everything is shown in the hospital. That's also an IoT device. All of that, exactly, all of that could be in a position of being vulnerable. Let's say, I'll just give you an example. Like we take a hospital for an example. There, if somebody gets in and somebody is changing the vitals, these could literally mess up the mindset that the doctor has behind treating that specific patient. It could cause devastating results, and don't really want to be in that position. This is why this is very important. Like a few years ago, people didn't really think about mobile pen testing. Now we do. Now we do, because we realize that yes, this is happening and this is exploited in the wild, and it should be something that we should look at. So today we'll be introducing you to IoT in that manner. So agenda for today is inside the box instead of outside the box, because generally what people do, hacking IoT routers via UART and chip off. So today we'll be discussing, as it says, we'll be discussing serial communication, how it works, what types are being used in the wild, and why exactly does it exist in the first place. So just getting started. Okay, as I already told you. So this is just tell me, what all IoT devices do you see in this specific slide?
Alexa.
So you got smart TV, you got Alexa, you got routers. What did you say? Yeah, this one. Oh, camera. Where's the camera? I don't see a camera. Okay, yeah, camera. Nice, good catch, man. Good catch.
That port is also
yeah, nice. Good catch. Okay. Anything else? Anything else you see here? Sorry? Vacuum cleaner. Nice. Vacuum cleaner. Good work. Anything else? Router. Yeah, already done.
6 devices are there.
6 devices. Right. 1 second. Let me just.
Smart socket.
Yeah. Good point, man. Yeah. So now do you see? Exactly. So yeah, smart sofa is basically devices. You could have a lot of speakers and all in it. There are sofas that have speakers in the headrest and things like that. Okay, so yeah, all of you said 6, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, bro. 10. You guys missed 4, man. What is this? Anyways, so yeah, you get a general idea, right? This is IoT. You don't really see it. It exists. That's the whole thing. That's why it's missed most of the places. So yeah, today we'll be talking about serial communication. So serial communication is what companies use to while they're building this. So that is used to debug Android applications and even Android phones itself. Here it is serial. It's the same thing. You connect it with cables to your computer, and it'll give you the output of the device on your computer. The logs maybe depends on how the system has been designed. That is what is going to display. So what companies do is while developing the device, they use this to debug it, to see what's going on, to see the logs, if there are any errors, things like that. Now when they are in production, they forget to remove these ports. So that's why serial communication is the first thing that we should look at when you're looking at embedded devices, because most of the devices, when you open them up, you will be able to see clear ports that you can connect wires to, and you will be able to get the logs, same as ADB. You'll be able to see all the logs. You'll be able to even get a reverse shell, not a reverse shell, sorry, a root shell directly. You just connect it to your computer, you press enter a few times, and then boom, you're in the root shell. That's the best case scenario, by the way. So this is why serial communication is something that is used as a debugging tool, but then forgetting that you need to remove it before production. That is one of the main things that you see when you look at pen testing a hardware device. So that, you know, this things should be disabled, because if they are not, then people will be able to get in very easily. A root shell is basically full access control. You don't have to do anything. So there are variations in it. These are not the only serial communications that exist. There are many others. Today specifically we'll be talking about UART, the first one, Universal Asynchronous Receive and Transmitter. So in that, basically, as I said, these things are communication that is present on the device. For you to be able to get that, you need to solder wires on it. Sometimes there are pins that are already soldered to it, so that you can directly connect jumper cables on it, and then you will be able to get a USB device. It's called a USB to TTL adapter that you will have to get. One second, I'll just show you that. I hope people are able to see this. This is a USB to TTL adapter. So as I said, jumper cables need to be connected to the device, and then those jumper cables will be connected out here onto these pins. Okay, once they are connected, you connect this to the PC, and that's how you get serial communication working on these devices. So this is used for a few of those protocols that I mentioned out here, but there are few who require more cables than these four. So for demonstration, these four cables are, one is your power, which is VCC, and one is your ground, which is ground. So those two cables are general. They are present in most of the communication standards that were mentioned here. And the two that we are going to be looking at today, which is specific to UART, is the transmit and the receive. So transmit and receive is basically exactly what they say. Transmit is something that transmits information, and receive is something that receives information. So generally what you would think as to connecting these things, you would directly connect, let's say, ground to ground, power to power, transmit to transmit, receive to receive. That would be wrong actually, because if two devices are transmitting together, they will not be able to read each other. So the connectivity between this, let's say an embedded device, and this should be power to power, ground to ground, transmit to receive, and receive to transmit. Because here if you send commands, they will be able to receive it on that device, and if they are sending certain logs, you will be able to receive on your computer. If you do transmit to transmit, that's going to just mess things up. So that is one thing that is different in terms of how you connect this to an embedded device. So yeah, for context, okay. So yeah, do you see this? One second. Yeah, you will be able to see it here. You see 5 volt. You see ground. That's XRD. That's receive. That's TX. That's transmit. That's 3.3 volts. You see, these are general pins that you would connect in UART communication. In other communications like JTAG and all, there are like 6 to 8 pins that you would have to connect. And there was just a side quest. This is there was an example when Checkra1n was released. I'm not sure if you guys are aware of that. It's a iOS vulnerability that gives us a jailbreak on any iPhone based up till iPhone 10. It's a hardware exploit that was exploited in the USB ports firmware, the USB port on your iPhone, this thing. The driver for this, the firmware it is running, that was vulnerable to a certain exploit, which was then converted into and built upon to get to the entire jailbreak. The reason I mentioned this is because using that exact jailbreak, it's possible to get JTAG connections on your iPhone itself. So you could get like ADB shell you get on an Android, you could get JTAG on here. JTAG is a little more complicated to deal with, just a side quest. That is what you could do with. So see, as I told you, IoT devices, the software of the charging port module is in question here, not the iOS firmware or anything else like that. That should have been tested. It was not, and that is the reason why we were able to get all of this, and that is the reason why they had to discontinue phones before that hand. That's the reason why we have jailbreaks on every single iOS version, which is good actually for iOS pen testing.
Exactly. So likewise, if you are into iOS pen testing and what he said about this jailbreaking part, the whole jailbreaking process is actually going to be covered in our iOS pen testing bootcamp, which is launching on 2nd of August.
Yes. Atharva Nanche is the one who is teaching.
He's the
Great guy. Yeah. Anyways, moving on. So these are the 4 cables we need right now. And as I told you, most devices, if you just open them up, you will be able to see that there are 4 pads that you could solder things onto. To a novice person who hasn't really looked at PCBs a lot, will probably be confused about which pads needs to be connected. But after you have seen it certain times, you'll be able to figure it out. It's quite simple. I'll just show you that practically right now. So let me just get this router. Okay.
That reminds me of a dental checkup.
Nice. So yeah, as you can see, there's a lot of things going on here. All you guys, I'll just give you a brief information about what these guys are. So this is basically your MediaTek processor. That's your Wi-Fi module of the router itself. That's the memory that we're looking at. This is a NAND flash module. There are different kinds of memory we look at. There's a lot of different kind of memory that we generally see. There's eMMC memory, that's NOR memory, that's NOR flash memory. Then this is the one that we're talking about right now. All right. So as you can see, there are a lot of things going on here, but only open ports you see are these 4 things. You see these 4 pins that are not soldered. Okay. So 4, that is generally UART, because as I said, power, ground, transmit, receive, 4 pins. Okay. So what I'll be doing right now is I'll be just soldering some wires to it quickly. Okay. So these are jumper cables. What I've done is I've just chopped off one end of it on this set. Okay. So as you can see, one side is your normal jumper thing and the other is chopped off to connect to this. I'll just solder it quickly for you guys. By the time you guys can ask some questions, I guess. Nice.
Hello. So everyone's catching up. Anyone has any doubts till now from Shaan? Not really, right? So I would like to ask some questions over here. Just a sec. So why do you think that actually students struggles to get cyber security jobs even after multiple certifications? Option A is lack of practical hands-on skills. Second one is the inability to communicate findings clearly. Third one is actually a weak understanding of real-world attack chains. And the last option being all of the above. Could any one of you please give an answer to it? But any specific one? You could raise a hand. Yeah, sure.
might not be. Hello. Hello. So might not be the answer in the options, but there are some hiring filters for 2 years experience for basic roles.
Okay, but could you go for the ones in the set as well? I appreciate it. Obviously, there are different answers as well, but something that you could
All
find
of the
in the
above.
question set.
All of the above.
All of the above. Okay, amazing. And guys, please clap for each and every one. And I would like to pass you all the coupon code as well for the RS test. What's your good name again?
Rehan.
Alright, so okay, so the next question, hello. The next question goes like, what should an ideal cybersecurity course lab include? First one, is it the simulated enterprise networks with layered defenses? Second one is random capture the flag challenges only. The third one is guess the password minigames. And the last one is generic web hacking forms only. Any guesses? Anyone from you? Yeah. Just pass on the mic to him. Introduce yourself as well, and then you can give the
I already introduced now.
Just your name and
Oh, Sahil More.
okay, Sahil.
Yeah, simulated environments where the first,
Yeah.
yeah, where the newbies can understand the overall architecture or the functionality of the applications, and then they can understand the flows, and then they can try to exploit the vulnerabilities. So
Amazing.
that's
Nice.
the
Clap for you guys.
So as you can see, not really my best soldering job, but it's just does the job done anyways. So yeah, I've connected these 4 wires. Now the point is, sometimes you will be lucky enough to find these ports being named. As I told you, it needs power, it needs ground, it needs transmit, and it needs receive. So all of those things you might be finding it like we did on this specific device, like it's being named, right? You can see it, right? So it will be named here as well in some devices, which is terrible information to be provided to the public, but sure. So yeah, that is what you would get, and you would not need to figure out which cable is what. There are devices you could use to figure out which cable is what in case if there is, let's say, JTAG for an example, it has like 6+ cables in it. It will be difficult for you to debug that which cable is what. There's a device called logic analyzer or JTAG, sorry, JTagulizer, something like that. You connect all of your cables to it, and then you basically put it in a logic analyzer, and it'll give you which thing is what. Okay. Today we'll be doing that manually. Since there are only 4 cables here, we'll be able to figure that out easily. How do we do that? We just take a multimeter, we put it on flow mode, which is this mode, which shows you if electricity is flowing from one end to the other. You see the arrow points there. Okay, and if you hear a beep on here, or if you see 1 or 0 here, that means electricity is flowing. Okay, so I'll just do that quickly. First we'll just try out, let's say, the first connector that we have out here, which is this one second. Okay, so we have the first connector. First, what we do is we try to find ground. Reason for that is because if you have ground, you can figure out most other things as well. Like if you have ground, then you can figure out which is VCC, because if you put one end on the ground and one end on VCC, voltage will be transmitted. So you'll see that on the multimeter directly. So what we do firstly is find ground. Okay. So for that, we're just looking for a beep if for this, one second. Huh? So this right here is the power pin for the router. As you can see, it's the power pin for the router. You connect the power here. So one of this is your ground. Okay, just try randomly which one it is for now. Okay, because if we try out all 4 pins and nothing beeps, we know the one that we are testing out here is not really the ground one, because it would have beeped otherwise. Okay, so now testing the first one just for an example. Okay, putting one end there and one end here. Okay, one end here. You see, I'll be just testing the first one now. Okay, nothing shows up, no sign. Okay, you see, beeps. Second one beeps. I'll just show you guys. इसपे क्या दिखता है? Can you hold this here? So whenever this is connected, You see it beeps. Shows 000 and beeps. That means current is flowing between these two wires. And these two wires are connected both to ground. Okay. So now we know that the black one out here is ground. We want to figure out the rest. How do we do that? As I told you guys, if you have ground, then you will be able to figure out VCC, which is power as in voltage. So if you put one pin on ground and one pin on anything, and if it transmits a sustainable voltage, that means that is specifically VCC. Okay. For us to get any voltage whatsoever, we would need to first power on the device. So what I'll be doing right now is just plugging it into power, and be a little careful with this. Sometimes if you get devices that are not really protected well, you will be shocking yourself. So yeah. Okay, it's powered on. As you can see, the LEDs are lighting up. I'll just give it a minute to boot. You see, it's powered on now. Okay, so I'll put the black one on the ground, and I'll put the red one and test each one. Okay, for that, because we want to now measure voltage and not just if electricity is being conducted from one end to the other, we are going to switch our modes, and we are going to switch to, so by the way, this symbol you see here is for DC, and this is the specific range that you want to measure. The voltage range, as in this is the smallest you could start, and it goes higher. As you could see, if I just turn there, you see there are the dot is gone right now. This is just milliamps. This is your voltage. You see now you can see, let's say if it's 3.3 volts, then 3 will be here and 30 will be here because beech mein point hai. You see that's how you measure voltage here. Okay. All right, now if I just put one end on ground, the black one on ground, and I test all the others. Okay, 1 second. Okay, and that's a bit weird, but okay. So one end on ground and the other one on the first pad. 1 second. You see 3.3 volts flashes directly. That's pretty much sure that that's the one that we're looking for. That's VCC. Okay, if we try any other port, then that shows this is 0. See, this is fluctuating. It is not really the one that we are looking for right now. All right, so this is the one that we're looking for, which is the first one. I'll show that quickly. 1 second. So okay, you see this is the ground one, the black wire, and this is the one that I was testing first, the red one right here, this one. So this is your power, the middle one, the second one from the start is your ground, and then now we need to figure out which one is your data receive and data out, which is transmit. All right, so that can also be measured in the similar manner that we found VCC. It is basically, as I was showing you guys, you might have seen one pin pad was fluctuating. So whenever you're transmitting data, it shows up in bytes, ones or zeros. Okay, that means the current will be fluctuating. So inherently, the fourth pin that I was testing, which showed up as fluctuating data, that is your transmit pin. Because it is transmitting data, the voltage is fluctuating. That is how you'll be able to figure out manually here. Then, as I said, will receive information, so it should not show any voltage whatsoever. And as you saw, one pin was not showing any voltage whatsoever. That's why we are now pretty much sure which cable is what. Okay, so we saw first cable you see out here is your power, the black one is your ground, the second red one is your receive, and the last one is your transmit. That's how the pin out goes here. Wow. Okay, anyways, so that's how the pin out goes. Now since I've already soldered these cables to it, I'll be just connecting that to the same thing on the USB TTL adapter that I mentioned earlier. As I told you, receive should go to transmit and transmit should go to receive. It's a cross connection since they should be able to communicate to each other, and no transmit should go on. Anyways, so yeah, I'll just connect that up quickly. Okay. So one more note, just a side note, what you could do is when this device, specifically this router, it requires a bit more voltage to run on. You can't really run it over a USB port. You can, but then USB port will be very hot, and some computers will give you a warning saying too much voltage is being drawn. So it is a better idea to just connect it to external power like it is right now connected to. And after you have done that, you don't need to connect the VCC cable, which is the power cable, because if you do that, then two voltages will be going to the same thing and it won't make sense. So generally, if it's a good idea, if it's a very small device, let's say you're talking about a bulb or something, and you've taken out the Wi-Fi chip or something like that off of that, and you're trying to get a UART shell or something like that on that specific device, then it will be very easy for you to just connect up the power pin here and just connect that to the computer, and that will be able to power that specific device. It's very small, it will not draw that much ampage. That's why it will be fine. Here it will, so I will be ignoring the power pin and I'll be just connecting the rest of the 3 pins up, just because the mentioned fact. Anyways, so I'll ignore the first one. I'll connect the ground, which is ground. I'll connect the transmit pin TX to our RX. I'll connect the, no, that's fine. All right, okay. So I'll connect the ground pin to ground. I'll connect the transmit pin to here receive. I'm sorry that you are not able to see that clearly. There's a heat shield on it. And the receive pin to our transmit over here. So 3 pins in total. Ground, our receive, our transmit, which is connected to receive here, and our transmit here, which is connected to receive there. All right. Now, as you can see, there's already a red light going out here, and you may also have a question about why we connect ground if you're not connecting VCC, because if voltage is already present on the device, why do we have to provide ground? The simple answer for that is ground needs to be common for both devices, otherwise there will be a lot of noise in it. The disturbance is caused because not all ground is of same resistance. If resistance is different, then current conductivity will also be different, which will cause a lot of data integrity issues and a lot of jargon to show up on your console out here. Okay, so now that we have connected the device, we can see there's a red light going out here because the ground is connected right now, and I'll just connect this to my PC now. So as you can see, there's some output going on here. This is basically what I was talking about. You can directly see the logs that are being generated by the router. If I disconnect and connect it back up again, it will start the router again. So you'll be see a lot of kernel logs and a lot of decompressing of kernel and a lot of things that are going on initializing the router. So I'll just do that once. I'm just disconnecting it right now and then connecting it back up. Okay, that's awkward. You see, uncompressing kernel image, and then it goes off. These are the logs that are generated when you are looking at how the system boots up. This is what you would see when you're starting up Kali. You might have, seen that in common. So yeah, this is what you would see. And as I told you, you can also get a shell via UART. This is just an Arduino IDE opened up with serial communication as monitored. That's it. That's nothing else, nothing complicated like that. Just looking at what things are going on. Now I'll show you guys, okay, how do we get a shell over here. Just open up putty, okay. I'm just going to close this. So actually one thing, if you guys are ever doing this and if you guys are ever using this kind of a device to connect your router or any other device to your computer, it will start giving you errors if you have two open applications that are listening on the same port. So it is a good idea for you to close one and then start the other. That's why I'm closing the Arduino IDE. Okay. And here in putty, I'll just go to serial communication. I'll do, okay. So if you want to check which, just go into device manager. Okay. And if you look into COM ports, you see ports COM, you'll be able to see Silicon Labs. This is the UART bridge that I was talking about. It is COM port 3. Now I know which port I am looking at. Okay, so I'll just do COM port instead of 1. I want to go to 3. Okay, and one more thing that I missed out about when I was explaining UART is the pace of information that is transferred from the device to our computer could be different. It could be a lot of variations. There are lots of default, like this is one, the one that is mentioned here is 9600. So speeds about devices that are transmitting from your, let's say, a router to your computer could be a lot of different things. UART specifically runs on a lot of different default speeds, and because it is not it is an asynchronous protocol, like as you mentioned here, it was asynchronous. Asynchronous means it doesn't have a clock. Generally, whenever you are talking about serial communication, there is a specific port that only spits out what clock that is used by the device. So that the rate of transmit. If you don't match that, your data will not be decrypted properly. That's why there is in most communications, you will find a serial clock as a port. Like we here saw transmit receive, there will be a serial clock. Now, since we don't have that here, we need to brute force that, or we need to figure that out. It is not very difficult. There are 2 or 3 variations that you generally try. One is 9600, another one is 115200, which is 1 lakh something something, and that is a default rate of transfer. And once you hit that, you'll be able to see the data clearly. Even in Arduino IDE, you will be able to you'll have lots of options about default speeds. I just choose one of those and just see if the data is being decrypted, and it will probably be decrypted because most vendors use generic rate of speeds. Okay, so here we'll be choosing which speed we are talking about right now. In this case, we are looking at 115200, which is 115200. Oh, 00. Okay, and we just do connect. Okay, it opens up a shell. Now guess what happens if I press enter? I get a shell, and if I just press ls here, it will list out the system. It will later. So here, this example is the best case scenario. It gives you a root shell directly. Now this is a busybox instance. Not really sure what you guys, if you guys know what busybox is. A general description of busybox is like a small binary, a single binary that is existing in the system that has a list of sub binaries which contains general commands that you would run in a Linux system like ls, cd, copy, paste, or copy, move, etc, etc. Now, depending on which vendor you're talking about and what functionalities they need, they will put up binaries in the busybox instance, and then they will compile the kernel. Here, if you want to list out what exact binaries that are available using busybox, you just write busybox. Just write busybox, press enter. It will list out all the commands that are available to you right now. So if I do that, yes, you see these are all the current commands that are functionalities that are available to us right now. Okay, not many things are available, like not even id is available here. If I type in id, it will show up command not found. Yeah, so apparently IPA works. So if I do IPA, it will list out the network adapters. You see, now from here on out, firmware analysis is what comes into play. Okay, this point is where you get to, is basically the golden thing. But after this, you do firmware analysis, but to get here, this is the best case scenario. Directly getting a root shell, zero protections whatsoever. Terrible security practices on TP-Link side of things, but yeah. So generally what you would do to protect UART is there are protections that you could put in place. There is something called obfuscation that you could do here. Like when the kernel loads, it loads an obfuscation module that obfuscates all of this traffic. So you are not able to decrypt that. You won't be able to see, even if you get a command shell, what are you going to do if you don't get any data out of it, right? There are ways to bypass that, which we'll be discussing further down the line. But that's one of the things that you could do. There's one more thing that you could block UART. You could block UART write. You can get read out of it. Like I was showing you logs in the beginning. You could do that. Logs tumko dikh jayenge, but you will not be able to type in commands. You will not be able to get this shell. And apart from that, you could just directly remove the pins. You could jumble the pins up. There's a lot of things you can do. But if an attacker has enough time and enough skill, they will 99% be able to get to the point where they want to get to, one way or the other. Yeah, that's the thing about hardware pen testing. There's nothing called 110% security. There's always going to be some guy who has enough time, who will sit there and just debug things until the time ends. Anyways, so yeah, now there are some ways to bypass those things as well, the protections that I was talking about. Like I was saying कि obfuscation hota hai, so the kernel module that loads obfuscation, what we could do is, once we just download the software update of this thing. Okay, we analyze that software, we derive the point on which the kernel loads the obfuscation module, and since we can listen to the thing, we will listen to it, and once we realize that yes, now the obfuscation module is about to be loaded, we just drop the voltage of the kernel. So the kernel doesn't load anything there, the code moves on, and then you pull it back up again, and then it loads the entirety of the rest of the code. So basically you just skip the obfuscation module. Yeah, that's how you bypass obfuscation. This one way doesn't really work always, but it is what we try. Next, as I said, you can block the write protections on this. You can block writing. Instead of that, you will just be able to read, you won't be able to write. For that, what we can do to bypass is, we have to figure out Here you will have to figure out which pin does what and do a little bit of recon on the chip and realize, okay, this pin is going to relate to that and that pin is going to relate to this. Once you are able to do that, 100% of the times there is a switch on that specific ports. On that switch, if you supply some voltage, if it exceeds a specific amount, it will let you write. If it doesn't do that, then it will not let you write. It's like a key. Vendors use that to be able to debug it themselves. अगर उन लोग ही नहीं कर सकेंगे तो फिर what's the point, right? That's why. So that's what they do, and that is how you can bypass these specific blocks that they put in. Like I ended up in a position where I was debugging a smart bulb. I had like 15 connectors on it. I had zero clue where to go, what to do. I connected all of these up. I tried to debug them. Nothing really worked for me. So yeah, that is one way. Now again, as I told you, if I had a lot of time on my hand and I could just go there and manually debug entirety of the whole 15-20 ports, whichever were in my hand, then I would be able to get through most likely. But then that's a lot of headache and a lot of things that you would have to do. It's a manual labor and it is not really worth the time. So that is where chip off techniques come into play. Chip off, basically, once you are in a position where you are like, okay, now I know this device does so and so thing. Now I know ये chip वो करती है, वो chip वो करती है. I want to read this and see what goes on in the back end. Like now we are able to get a shell. We will be able to navigate the environment and we'll be able to see what binaries are available. One second. Bin. Okay. You see all of these binaries, but as I told you, there's only one binary that all of these are linked to. Okay. You see, yeah. This is this BusyBox binary that you see that has most everything. Apart from that, nothing else has anything. Okay, all is 7 KB is all linked to BusyBox. You see, exactly. So that's the premise behind what BusyBox do. Whoa, it does. Anyways, so moving on to chip off. What chip off is when you take off the chip actually from the router or from the device and put it in a debugger and put it in a, let's say, one second, I have a memory reader out here. This is a universal programmer. This right here is a universal programmer. You put a chip inside this. There are lots of different variations of this you can get and lots of different varieties of how many chip pinouts that they have. This specific one is a 8 pinout because this chip has an 8 pinout. So that is a universal programmer, and that is what we use as a chip off tool to get the data off of the chip itself, since we won't be able to read it otherwise. Now we'll be moving on to chip off, and yeah. So yeah, basic generic thing is whenever you're doing chip off, it's because you don't get any serial communication to your device whatsoever, and it is too hectic for you to manually debug the entire thing. Okay. So moving on to chip off. For that, instead of a solder, we'll be needing a heat gun, because the chip that we'll be removing right now, as I said, this is your MediaTek processor, this is your Wi-Fi chip right here, and this is your NAND flash. This is where the data is stored. This is what we want. Okay, so we'll be taking out this chip today, and for that we'll be using a heat gun. I'll just do that. Okay. Yep, and here we have it. Yep. Okay. So this is the NAND flash that we are going to inspect today. The specific reason on why we took this out instead of any other thing is because this stores the entire operating system and stores all the binaries that we want to look at. Also, you would be able to see there's a dot in the upper left corner, right? That dot specifies where the pinout starts. So whenever they say first pin, the pin that is right beside that dot is where you start counting downwards. Okay, so like then that goes 1 2 3 4 ऐसा. All right, so that is important, because if you want to read that, you should be connecting the right pins to the right ports. Okay, now you're using that universal programmer. I'll just plop that in here. Okay, just open that up and plop it right there. Yep, that's connected. You see, The chip is connected, and as I mentioned, this dot you see out here, that dot should map to this dot. Yeah, you see that dot? That dot right there? That is also where the chip reader starts. Alright. Now, moving on to the practical itself. Now, to run this specific reader, you need a software called XG Pro. It's a software for this specific brand of reader. If you have a different brand, then they'll probably have a different reader in their own thing. Okay, this is the reader that I was talking about. Generally, how do you read data from here? You just press on auto to get an auto readout of what we have here. See, we have an 8-pin chip, so we selected 8-pin. We press detect. It will detect. Okay, so see SOP8. You see SOP8? That's because software basically it says 8-pin out ka jo hota hai, that's called SOP8. Okay, so we select that, we press select, and then we go on read. Okay, we press read, and then we press read again. Oh, just mentioning, you see there is no data here. It's FFFFFFFF, which is 0000000. Okay, just please read. Okay, it reads. Notice the background, see it updates. Now you're able to read all the data off of that. It won't make sense here obviously because this is hex. So what we are going to do is, as you can see, data is pulled out from the chip. What we are going to do is we are going to save that to a file. It's a bin file. I just rename that. Okay, desktop. Okay, yeah, just rename that to test. Okay, and save. Okay, now we have saved it in our folder. As you can see, test.bin. Okay, so to inspect this, there are lots of different tools you could use. I am going to use binwalk today, and that's where firmware analysis starts. This is the firmware of the device. You have extracted it. Now it will be a very simple argument about why am I doing so much mehnat if I could just go to TP-Link's website and download their firmware. The thing is, here I can go to TP-Link's website and download the firmware. It won't be possible on every device. Like I told you guys, that specific bulb that I was testing, there was no firmware download link for that. I had to extract the firmware, otherwise I was not able to get that. That is the reason why this technique is being showcased today. I'll just open up VirtualBox to get myself a Linux instance to get binwalk and everything working. Starting that up. Any questions by now? Any questions? What's up?
That is basically a modified ESP32, right? USB to
TTL.
UART.
Yeah, USB to TTL. You could make that yourself if you want. The USB to TTL adapter generally doesn't do anything much. It just converts the serial data that is coming out of the device and gives it to the computer that it can understand. The reason it is specifically this device is because there's a driver for it, and if that driver recognizes that yes, this data is coming through, then it will be able to basically translate us. This data means that in serial communication. That is why we use USB to TTL. Otherwise, we would directly be connecting that to a USB port and plugging that in. That would not have worked because then transmitting and receiving would have been different. Like I told you, the data that comes off of here isn't really readable directly. You will have to convert that through a TTL adapter. Alright. So it's not really modified anything, it's just a tool that we use. Anything else? Any other questions? Yeah.
When we are connecting the router to our laptop,
Yeah.
and it shows in console we show the log output.
Yeah.
Then while we are connecting this, it shows the output of connection also in the logs.
Depends. If it is configured to do so, it will. Like here, if you press the reset button, it will show up as reset button pressed. I tested that in fact actually when the log. So when the system is booted up, there's not really anything that is happening right now. So not many logs will be generated. So when I connected the device to test myself if the connection is correct, I pressed the reset button to see if it was going on. So you might have noticed that there was a reset thing that showed up when I connected it. So yes, it is possible that they show up, but if the manufacturer has said no, that should not be shown, only the kernel logs and the boot logs should be shown, then that will be shown. That's the thing. Yeah. Any other questions? Anything basic, anything like that? Any random question you want? Nothing? Good? Okay. Okay. Moving on with the practical. I'll just do a shared folder here. Yep, now it shows up. Okay, as you can see, we have our test.bin here. Okay, so what we are going to do is use this is general basic firmware analysis that I'll be performing. There could be a lot more that people would do, and a lot more security people have a lot more knowledge about firmware analysis that what we'll be showcasing today. Okay, so I'll be just running binwalk quickly. Okay, and with that I'll just check what's the structure of this specific firmware. Okay, so yeah, this basically shows me what the structure is. Now this shows me that this is a squash fs file system. It is in little Indian, it is a language, and it shows me the compression type, which is zip. It shows me the size of it. It shows me where exactly it is located in the binary itself. All right, this is a lot of data that you could use to extract some specific parts of the file system if you wanted to. Like squash fs is the system itself. It has all the binaries and everything what we saw when we got a shell through UART. If let's say for an example you wanted to do some research on the kernel or something, then you would do the u-boot wala thing. So that's the kernel of this specific router. Okay, you would extract this if you wanted to do kernel analysis. Let's say I told you there's a function in the kernel called console equals to log. If that is disabled, then you would not even be able to see the log here in the UART communication. So yeah, if you wanted to know all of that, if you want to edit that, if you wanted to change all of that, then this is what you would do. Okay, to extract this, we will just use -e in binwalk, which extracts the file system. Okay, apparently something went wrong. What? Okay. It's just shouting at me because I'm running it as root. Okay, it has extracted everything, and I'll be showing you guys. See, test.bin.extracted. It has extracted the entire file system. Okay, you see, now you see squash fs root. I'll just go in that, and as you can see, this is the exact binary that we saw when we got UART communication working as a shell. So this is where firmware analysis start. This is where you can go in and you can check each and every binary config file if you want to see a config file, something like that. Or you could just go into etc password, passwds. Sorry, one second. This no, okay, one second. ls, okay. Oh yeah. You see, password.back file. If I do cat, I don't think this is going to be in anything. Yeah, you see. So in fact, actually, this password you see out here is, if you try to crack it using hashcat, it will be 1234. I'm not kidding. I cracked it. It is 1234. So one thing that is different in terms of why we do something like this rather than just not the shell over UART, the shell over anything that is running is important. Why? Because all the kernel loading things will be done after the fact. When the system is running, that is when you will be able to do dynamic analysis. That is when you will be able to see what the file system looks like after booting up. Like now you can see, if I go into var, one second, if I go into var, there will be nothing there. Okay, see, there's nothing there. Var is empty. Var is filled up when you do when you took out a command shell from UART. If you go into var, you will be able to see a lot of files. In fact, there is also a password file there, which has a password for I believe it is drop bear. It is an SSH command shell ka password. The password is password at the rate 123. So yeah, a lot of things you could do. Hard-coded credentials. In fact, this router specifically has a CVE that showcases that 1234 wala password as a CVE itself. Hard-code credentials. SSH is running on this router. You could SSH into the router using password 1234. I think 1234. Yeah, it's brute forceable, I guess. Anyways, so this is firmware analysis, and you could go a lot further with this. Just this is the showcase that is going to present today. Now I have actually went further and up to a point where I modified the firmware, and in fact I believe this is the router that I modified it on. And if we go back and if we just go into sbin, we see a config file. Okay, if I just cat out, if I just nano into the file, okay, config, okay, here you can see, one second. Yeah, you can see at the end I'm calling a command. This is a basic reverse shell that I generated using MSF Venom shell code, and I implanted it inside the router, and I was able to repack it and then drop it back onto the router, and this is why we are getting it now, firmware extraction. Anyways, so going into the bin directory, as we saw, there is a backdoor. So this runs every time the router starts up, and it will give us a shell on port 1337. You just need to do a netcat connection, netcat space IP address space 1337, and you will be able to get a shell directly from there. This is the point where you could go to even further. After this, you could go to doing firmware analysis and learning about the firmware and finding vulnerabilities in the firmware. Vulnerabilities, like I just mentioned, hard-coded credentials, some configuration files that is loading up a vulnerable binary, something like that. Anything. This is now, you could do whatever you want. You have root access on everything. This is why it is very important for you to test all of these devices. This is why it is very important for all of these devices to be noticed and conducted as an audit. Because if it is not, then you're going to find all of these devices like this. One more thing, when you repack this firmware, due to time constraints, we'll not be discussing about how exactly to repack and everything. But if you are able to repack the firmware and change the signature of it, TP-Link will allow you to upload that firmware to the web API, web UI, and run that as the firmware, and then you get the backdoor installed, and then you will be able to connect to any router whatsoever. You just give me a TP-Link router that has this specific model, and I'll upload that firmware. It'll give you a shell on port 1337. So yeah, that's why it is important for all of these IoT devices to be noticed and to be pen tested. So any questions? I actually wanted to show you guys the shell, but I think it's just too long. I just have to resolder the entire thing. Yeah, what's up? No, it is, one second, I'll just show you the model number. It is TP-Link WR845N. It's a basic router. I have it at my home. I'm not kidding. I am literally using this at home. It's very sensitive information. Please don't disclose. But yeah. Anyway, so any questions apart from that?
The baud rate of the device. Have you seen any other baud rates other than 9600 and 1152?
I have seen 8,000 के अंदर एक range, I believe. There's a lot of things. So the logic analyzer that I told you, you remember JTagulator? There is a device called JTagulator. You use that to analyze which pin does what. Now when you do that, it will also give you analysis on what exact baud rate it is looking at. So yeah, that is easier to figure out. You just Google it up, you will be able to find that easily.
You can also Google the IC and will they have it?
Yeah, you can actually find the data sheet of that IC, and that will show you what exactly it is. But one more thing, as I told you, the same example, the bulb that I was talking about, that bulb, the IC that it had, I Googled it, I tried the entire thing, I was not able to get to the data sheet whatsoever. Now I'm stuck on that. Anyway, so yeah, you would be able to do that. Baud rate is quite easy to understand. You just try multiple things and it will just work out. In fact, in the logic analyzer software, it has a brute force functionality that you can use. So it will brute force go through a few of them, and then it will tell you which one it could be. Okay, so yeah, that's the demonstration for today. I hope you guys liked it, and I hope you guys learned.